mass moving to the right at 4 meters per second. It, in front of it, or it is pursuing a 10 kilogram mass heading at 1 meter per second, also to the right.
Okay.
They will collide in a perfectly inelastic collision. If ultimately it'd be what is the final velocity.
Okay.
And one hint, and some students miss it at all levels, unfortunately, at any level, unfortunately. When I would say what is the final velocity, that is singular, to imply that there's only one answer. I've had students come out with two different answers, and I will tell you, if objects are stuck together, they will go at the same velocity. At least in physics 110, and 251, and 151.
So with that last question, all we would have to do is just add the weight of them.
Oh,
No?
oh, what did Monica say that made me go, ooh?
The weight.
Yes, what should she have said?
Mass.
Thank
The
you.
mass, yes.
Yeah, okay.
So we just add the mass of the two boxes and plug it into that equation to find the final velocity.
Yep.
We wouldn't need to do,
But we still had to do all that to get to the 22.
oh, yes, okay. Okay. Now I understand.
So I broke it apart, so it would be, what's the momentum of the 3 kilogram mass? What's the momentum of the 10 kilogram mass? What's the total momentum
Gotcha.
before the collision? What's the total momentum after the collision? Same answer.
Hmm.
And then what's the final velocity?
Okay.
All right, let's take a small little break here. I know that we're done in 25 minutes, but let's take a small little break. We're gonna come back, refreshed, ready to go, and deal with a problem that's very much like this, but just slightly different, enough to throw some people off. And I'm gonna pause this and pretend I'm gonna remember to turn it back on. Oh, also, and I can't do this with every physics 110 class. If I don't teach the lab, I can't do this, but if I have the class and the lab, I also will go through, and if your lab grade will help your class grade, then I'll include it, and if it doesn't, I know. All right, same problem, except for the 10 kilogram mass is now heading to the left. I hope you at least have some sense that there's going to be something different. I mean, one pursuing the other one versus a head-on collision, we should expect somewhat different results. So let's do it the fun way, with math. So let's start out with the initial momentums. The momentum of the 3 kilogram mass initially is
12
you want to throw some units into that?
kilograms times meters per second.
There we go. You made an assumption. What assumption did you make?
Me?
Yes. Other people, what assumption did he make when he just gave you that answer?
The momentum doesn't change for the first box.
Assume that, I guess that would bundle into, assume that the problem was written up correctly. All right, we'll get to the next one and then we'll come back to the assumption Brian made. If any of you have an idea of what the assumption he made is, the same one was made over there, but I just didn't pursue the question. All right, so the momentum of the 10 kilogram mass initially is
-10.
What assumption did Brian make when he told me 12?
To the right is positive.
Yes. As soon as he established this is to be 12 and not -12, at that point he said that to the right is positive. Which forces the second one to be negative because it's going in the opposite direction. I have only two vectors here in this equation, so they have to have the same sign. So if velocity is negative, that's negative. If velocity is positive, that's positive. All right, so now, what is the total momentum before the collision? I hope everyone in here has an answer. Matter of fact, I'm just going to point randomly on the sheet here and see whose name comes up. Jennifer, what is the total momentum before the collision?
-12.
Said negative 12?
Yeah.
No, not quite.
-22?
Not negative 22. How did we get 22 over here?
22.
Adam.
Yeah, so what would be over here?
2.
2. Yeah, just 2. 12 plus negative 10. What is the total momentum after the collision?
2.
Yep, it's the same. So the total before equals the total after. Again, that whole idea of conservation in physics, that's a physics conservation. Same, the total doesn't change. And after the collision, it's a perfectly inelastic collision, which means what's gonna happen?
Stick
They're
together.
gonna have a perfect elastic equation.
I heard some very quiet answers. Brian, I heard you first.
They stick together.
Yep, that's it. Is that what you were saying, Jennifer? All right. So they're gonna stick together, so it's now one happy family of mass. What is the total mass now?
13.
Kilograms. Times the final velocity. And so the math problem is 2 is equal to 13v. That's the math problem we're dealing with here. How do we isolate v? I think you said
Divide by
13, but I'm not 100% sure. You were very quiet. Did you say 13? Okay. And so whatever 2 divided by 13 is, my final velocity,
1.54.
0.154.
0.15
0.154.
Meters per second.
meters.
Our answer is positive, which means that after the collision, it'll still be going to the right. I will say that conservation of momentum is incredibly powerful. It has a very good advantage in the fact that over conservation law we get in the next chapter, in the fact that they're vectors, so we don't lose information about the direction. It has the complicated matter of the fact that it's a vector, and so we don't lose information about the direction. In the next chapter, we'll deal with a conservation law that deals with scalars, where we can ignore direction. So they each have their pluses and minuses.
What were you saying about the momentum equation and if they're both positive, they're both equaling each other? The P
Yeah.
hat equals M times
Where-
above momentum. That.
No, oh,
You pointed to
That-
it and you said,
I have 2 vectors in here. I have a vector on each side of the equation.
yeah.
Since I have only one vector on the left and one vector on the right,
Mhm.
and vectors have direction, they have to be in the same direction.
So they both have to be positive or both?
So they're both positive or both negative.
Okay, but in this one, we had one negative.
The momentum, the velocity was positive, so the momentum of this was positive.
Oh,
Here, the velocity is negative, so the momentum was negative.
okay,
That's, so looking at the individual values.
okay. Gotcha.
All right, same type problem, just slightly more complicated. Yeah, feel the energy. Answers in unison will be really cool when we get there. We'll stick with our familiar 3 kilograms mass going to the right at 4 meters per second. The 10 kilogram mass, let's have it go to the right at 1 meter per second. This time, they're not gonna stick together. After the collision, the 3 kilogram mass is, let's say it's gonna go forward at 2 meters per second. And what I want to know is that 10 kilogram mass what is its final velocity? In other words, V final, V10 final. We're gonna start out the same place we did before. What is the momentum of the 3 kilogram mass before the collision?
12 kilograms times meters per second.
So P3 initial 12 kilogram meters per second. What assumption did Brian make?
Moving in a positive direction.
All right, then P10 initial equals. Therefore, the total initial momentum is,
22.
all right, now saying kilogram meters per second is sort of a nuisance, writing it down, all those letters. If you want to do a shorthand, there is a way. You can make up your own unit, but there are rules. If you make up a unit, do not pick a letter that's being used for something else. Do not use a capital N, because that stands for newtons. It would just be very confusing. I heard one person, I went to a lecture where someone suggested capital B for Bechamel, or I forget the guy's name. I prefer capital D personally. We don't use capital D for any other unit. And so you got the 3 lines like this means I'm defining it. It's true by definition, and I'm defining it as a kilogram meter per second. Since I have made this up, this is true only as long as it's on the board. If I use the capital D over there and then I erase this first, then suddenly that's wrong over there, because this is something I made up on a quiz or test if you want to do it. If you put this at the beginning of the test, I will assume it works for the rest of it. If you put it on an individual problem, I assume it's true for that individual problem. In computer science, that would be global variable versus local variable. Or stick with kilogram meters per second, which some people do. What is the total momentum after the collision? This would be a good place for in unison. Total momentum after the collision.
22D.
Sounded like a single voice. It was that in sync. That was impressive. It would indeed be that. Oh. Now, they're not stuck together, so I can't do a combined mass, but I can figure out, well, I know P3 final. What is the final momentum of the 3 kilogram mass?
12.
6.
Not 12.
6.
I heard someone just say it.
6.
Because after the collision, it's going 2 meters per second. So 6. So therefore, what is the final momentum of the 10 kilogram mass? I know they have to add up to 22.
Oh, okay.
What'd you say?
I said, oh, okay, now I understand.
Okay.
D. Oh, okay.
Yeah, I did a very subtle and cool nod that apparently
Sorry, I
you
didn't see
missed,
it.
as my coolness generally is missed. So 16, I assume. My total before has to equal the total afterwards. That lost 6 units, this gained 6 units. All right, so I know the momentum, I know that's gotta be equal to the mass times velocity, so that's gonna be equal to 10 kilograms times my final velocity of the 10. The math problem I'm working with is 16 is equal to 10v. That's my math problem. What is the final velocity of the 10 kilogram mass?
.6 meters per second.
And we use 10 because that was the mass of the
Yeah,
first. Okay, but
Couple things to point out. The change in momentum of the 3 kilogram mass. What is the change in momentum of the 3 kilogram mass?
2.
Magic 2?
4 minus 2.
That would be the change in velocity, change in momentum.
6.
Close. Yeah, I guess the other one was not 2. You had the same mistake both times. Final minus initial.
16 minus 6, 10.
No, the 3 kilogram mass. We go from 12 to 6.
6. Negative 6.
Negative 6. Negative 6 kilogram meter per second. All right, the change in momentum of the 10 kilogram mass. Went from 10 to 16.
Positive 6.
I think you said positive 6.
I did.
In a conservation problem, whatever one loses, the other one gains. All you're doing is transferring it from one object to the other. And one final idea here. When we did that derivation, it would have been nicer had I not erased everything, but most of you took notes on it. We started out, we had force A on B times the time. We did a whole bunch of steps and we eventually got down to PA final minus PA initial, which is just actually, so, and then we went from there. But this is just final value minus the initial value, that's the change in momentum of A. So this force times time is equal to the change in momentum. So if I told you, you know what the change in momentum is, if I told you how long they were interacting, you should be able to find the average force that they applied to each other. However, this has a special name, force times time or change in momentum, because that's obviously too much of a mouthful. They needed a single word to describe the change in momentum, or force times time. And now for my most obscure clue. It was the name, oh wait, no, try that one again. It's from a commercial in the 70s. If someone suddenly buys you flowers, that is called?
Suddenly buys you flowers.
A gift.
Impulse.
Impulse.
Perfume.
Oh.
Impulse. So if you're given a question and asked what is the impulse of imparted or the impulse applied to object A, if you know the force and time, you multiply that. If you know the change of momentum, you do that one. So the impulse on A was negative 6 Descartes. The impulse on B was positive 6 Descartes. Yeah, still written up there. And for those who, I'm saying Descartes,
Oh, okay. Descartes.
the French guy, I think therefore I am, that Descartes.
Okay.
He did work on momentum. When Newton was doing work with forces, Descartes was working on the momentum point of view. Anyway, if we get snowed out on Thursday, look for a message about Plan B or Plan A. No, I guess Plan A is here. So if we start getting snow days, just look for announcements. And on that note,
enjoy the snow.
I hope it does.
Stay warm.